All right, everyone. So I guess we are live now. And welcome back. A very good evening to you all. So kindly write a +1 if I am audible and equally visible to you. Well, so how many problem you were able to solve? And before starting the discussion, I want you guys to rate the entire contest on a scale of 10 so that we can improve the problem set. And yeah, rate the entire contest on a scale of 10. And if you are rating less than or equals to 3, then please justify your reasons. That would help us to improve the upcoming problem set. And I personally categorize the entire contest from easy to a medium level. And all the four problems were doable. There is no prerequisite at all. And we'll discuss the solution of all the four problems. Cool. So everything seems good to me. Let me share my screen. Okay, so yeah, this is the perfect template. So starting with the first problem, you are given an array ARR of non-negative integers, and you have to find the number of pairs of indexes I comma j such that I is less than j, and ARR of I is a complement number of ARR of j, and here a complement number of x is the number formed by changing the digit of x to its complement and removing the leading zeros. So the complement of the digit is the difference between 9 and that digit. So complement of digit d would be 9 minus d. So for example, the complement of 1 is 9 minus 1, which is 8. The complement of 2 is 9 minus 2, which is 7. So for this array, there exist two pair. This 1 and 8 are complement of each other. Then this 4 and 5 are complement of each other. So the expected output here is 2. Now let's see how we can solve this problem. So we have digits from 0 to 9. So here the complement of digit 0 is 9. The complement of digit 1 is 8. Then the complement of digit 2 is 7. Complement of digit 3 is 6. The complement of digit 4 is 5. So in short, the complement of digit d is equals to 9 minus d. 9 minus d. So let's say we have an array of size n, and the idea here is to fix every index j and find how many possible values of index I exist. So let me write in this way: a1, the first element of the array, then a2, a3, and I'm also using one base indexing for explanation purpose. Then index a of j, then the last element of the array a of n. So now I'm going to fix every index j and will find the number of possible values of I such that a of I is equals to the complement of j, complement of integer a of j, right? So basically we need some information from the left half, and that's why we can build this array. We can build the information in a progressive order, starting with the value of j is equals to 1. Then I need to do a lookup. So for that I can use a map data structure. So integer map of integer comma integer, where the key will be element and the value will be its frequency. Now let's just first check how we find the complement of some integer a of j, and then I will do a dry run. So let's say a of j is equals to 8 4 3 2. Cool. So here in this case the complement of this number. So to find the complement of digit, we all know the difference from 9, that is 9 minus 2. The complement of this digit 9 minus 2. And also I need to multiply it by 10 power 0, because this is the digit which is at ones place. Then for here it is 9 minus 3 multiplied by 10 power 2, because this digit is at 10 place, 10th place. Then in this case 9 minus 4 multiplied by 10 power 4, 10 power 3, then 9 minus 8 multiplied by 10 power 4. Cool. And now if you add these values together, then you will get the complement of a of j. And let me write a pseudocode also for this. So let's write a function and name this function as a complement, and this function complement will take one integer n and it will return me the complement of n. So the very first thing, let's initialize the complement with 0 and also the power, basically the position of a digit, and this is equals to 1, because the first digit is at ones place. So this would be 10 power 0, then 10 power 1, then 10 power 2, and then 10 power 3. Cool. So that's why 10 power 0, which is equals to 1. Then while the value of n is greater than 0, every time I will add the corresponding digit, the complement digit. So that would be previous complement. So complement is equals to remainder. And how I get the digit? Basically, every time we remove the digit from the end, and by taking a mod with 10, and basically the remainder would be n mod 10, right? And now we have the digit, and I need to find the complement. So I will simply take 9 minus this digit, and my new value, my complement up to here would be 9 minus this remainder and multiplied by this power, and then I need to add complement. Cool. And finally I will multiply the power with 10, because in the next iteration we process the next digit. So power multiplied by 10, and I also need to and I also need to remove this digit, the digit which is at the ones place from integer n. So n is equals to n divided by 10. So this is the way you can find the complement. There is an edge case. It might be possible when the value of n is equals to 0. So in that case you need to return 9. This is an edge case. Cool. And once you get the complement, just simply check in a map that how many previous value we have which has value equals to this complement of a object. So yeah, this is the way we can solve this problem. Now let me quickly do a dry run for some particular example. Okay, maybe this example one, 8145. 8, 1, 4, and 5. So I will declare a map. You can also use unordered map, dictionary in Python, tree map, or hash map for the Java users. So int map of integer comma integer. And the key will be value of element, and here I will store the frequency. So let's call this map as MP. So initially it is empty, and we start with the value of j is equals to 0. That is first index. So here in this case, what would be the complement of 8? So the complement of 8 is 9 minus 8, which is equals to 1. Cool. Now in my map, I'm going to check how many integers previously we have seen whose value is equals to 1. No such integer, so my answer will remain 0. Initializing the answer with 0. And then I'm going to add this integer in my map because it might be helpful in future. So the frequency of 8, which was previously 0, and now it is equals to 1. In the next iteration, tell me the complement of 1. So the complement of 1 is equals to 8. Now this information I will get from my map. How many integers we have previously seen whose value is equals to 8? One integer, right? So I will increment my answer by 1. And then we'll add this integer in my map because it may be helpful in future. So MP of 1, previously it was equals to 0, now it is equals to 1. Take me to the next integer. So the complement of 4. Okay, in human entity is saying we can do it using hash map. So see, you can also solve this problem with the help of an unordered map of C++ or hash map of Java. But using the unordered map or hash map is not a good idea because internally they uses hash table, and due to the collision in the hash table, the time complexity, the worst case time complexity is linear. But in case if you are using a map, then the worst case time complexity is always logarithmic. On an average, it is constant, but in the worst case, it can be linear. That's why what I generally suggest you to do not use the unordered container or hash map or hash set during the contest. If you are an interview, then it's good to use these containers or these data structure, but during the contest, never recommended. So the complement of 4, and it is equals to 5, 9 minus 4. Now I'm going to check how many integers previously we have seen whose value is equals to 5. No such integer. So I do not increment my answer. And then I'm going to store this value. MP of 4, previously it was equals to 0, then change it to 1. Cool. And in the next iteration, we are at this integer 5. So the complement of 5. So the complement of 5, it is equals to 4. Now I am going to check how many integers previously we have seen whose value is equals to 4. And this will be given by this map data structure. So I will increment my answer by MP of 4, and MP of 4 is equals to 1. So now my answer is equals to 2. Then I will store this information. I will increment the value of 5 in my map because it might be helpful in future. So change it to 1. Cool. And after this, we reaches out of bound, and my answer is equals to 2. And this is same as the expected answer. So the time complexity of this solution would be order of n multiplied by log of n base 2. And this log of n base 2 because of a map data structure. A space complexity is linear because of a map data structure. So write a quick lesson if it is clear to you. And let me show you the implementation. So this is the method that you need to complete. Count pairs. Here I have declared my map and initializing the answer with 0. Then fix every index j. Now I am going to check how many possible values of I we have. So in my map, I am going to check how many previous value we have seen whose equals to the complement of AR of j. And for this, I have this function complement of AR of j. Cool. And yeah, I already told you how we find the complement of some number. So the time complexity here is n log of n base 2. And one thing I forgot to add, the time complexity of this complement method. The time complexity of this complement method would be log of num base 10. So yeah, this will be the final time complexity. Base 10. Here the base would be 10 because every time we are dividing the number by 10. So that's why base 10. So this will be the total time complexity. Final time complexity. The time complexity here is n for a for loop, and then log of n base 2 for a map, and multiplied by log of maximum integer of the array and base 10. So the maximum integer of the array can be up to 10 power 9. Cool. So log of 10 power 9 and base 10. This will be the time complexity. And I hope it is clear to everyone. So write a quick plus one if this solution is clear to you. Today I couldn't solve second problem. Okay. Don't worry, we'll discuss the solution of the second problem just right after this. So before that, write a quick plus one if it is clear to you. So coming to the second problem of the contest. This one. Total ways of a maximum or. So in this problem, you are given an integer n, and you need to find all the integer x such that x is less than or equals to n, and the value of x or n is maximum, and you need to return the count of all such integer x. So for n is equals to 4, to have the maximum value, there will be 4 possibilities for x. second question got passed in order of n, even though the constraints were up to 10 power 9. So maybe because of the weak test cases, we'll report this issue to the problem setter team. Alright, so now let's discuss the solution. And we also have a follow-up version of this problem, the last problem of the contest. So let's say we have some integer n, and whose binary representation is 1, 1, 1, then let's say 0, then 1, and let's say 0, 0, and 1. So what could be the maximum value of n or x? So the maximum possible value of n or x is having all the bit set after the most significant bit of n. So that is, this is the configuration for the maximum value of n or x. Now I need to find how many such values of x exist, and then I will. Okay, so at this point of time, I'm only interested to know how many such value of x exist. Then I need to consider the second constraint, that is value of x must be less than or equals to n. So first let's find how many total values of x exist, which lead me to the maximum value of n or x. So the very first thing, the position at which the position at which bit is 0 in n must be set. Then only the result would be 1. So this bit in x must be 1. Then this one also must be 1, and this one, and for the last bit it is 1. So I can pick any bit that is either 0 or 1. So that is the bits in n which are 1, and for these corresponding bit in x we have two possibility. That is, here I can either pick 1 or 0. Here also I can pick either 0 or 1. Here also I can pick either 1 or 0. For this position I have two options. For this position also I have two options. So in total, how many possible values of x? So in total, the possible values of x is 2 power the number of set bits. The number of set bits. Now I need to consider the second constraint, that value of x must be less than or equals to n, because in total we also taken those values of x into an account which are greater than n, and I need to remove the count of those numbers, those values of x which are greater than n. So let's see how many possible values of x are there which are greater than n. These are my extra count, and I need to subtract this extra count. So here in this case, let me again draw the value of n, write the value of n. So three ones, then we have 0, then we have 1, then 0, 0 and 1. Cool. So try to pay more attention here. So we all know if the bit is 0, then the corresponding bit in X must be 1, right? Must be 1. And before this, we have some prefix. Before this, we have some prefix and prefix of ones. So all the values of X are greater than N, which has this prefix. Try to pay more attention. All the values of X are greater than N, which has this prefix. That is 1, 1, 1. Cool. All the values of X are greater than N, which has this prefix. Because so what I can say, for the prefix we have only one possibility. And now for this integer, what I have considered, for this integer I have taken two possibility, that is either I pick 1 or I pick 0 for this position. Either I place 1 or 0. Then for this position I have only 1, and basically this position is fixed where I will place only 1. I cannot place 0, otherwise the resulting value of X would not give you the maximum result. Then at here also we have only one possibility, and for this one I have two possibility. So what I'm trying to say, I need to count this extra. So let's find the position of the first 0 from left to right, that is MSB to LSB. And before this first 0, I need to know how many ones we have. So let's call this as a prefix. So basically these many ones we have, and how many ones after this we have. So this is nothing but the total number of set bits minus prefix. So total number of set bits minus prefix. So set bit minus prefix. So the values of X which are greater than N is 2 power number of set bit minus prefix, the number of bits before the first 0. So yeah, this is the complete solution. So in short, my answer is equals to, total minus extra. So write a quick +1 if it is clear to you. This is the complete solution. First, I calculated how many possible values of X are there, which lead me to the maximum result. And then first I calculated the total values of X, which lead me to the maximum value. That is, how many possible values of X are there, which lead me to the maximum value of N or X. And this is the maximum value of N or X. The configuration, that is, all the bits are set, all the bits are 1 after the first MSB. After the MSB, this is MSB, and all the bits are set in N or X. So how many possible values of X are there? So 2 power the number of set bits, because the position at which we have 1, I can place anything, either 0 or 1. But the position at which the bit is 0, the corresponding value in x must be 1 to get the maximum result. So here we also consider the values of x which are greater than greater than n. But in the problem statement, it is clearly mentioned that a value of x must be less than or equals to n. So how many possible values of x are there which lead me to the maximum result and greater than n? So let's call this as a let's call this count as extra. So my answer will be total minus extra, that is possible values of x which are greater than n. Cool. So how many possible values of x are there which lead me to the maximum result and are greater than n? Greater than n. So consider the occurrence of first zero from left to right, that is from MSB to LSB. So this is the first zero, right? So let's call this position as P. So we all know to get the maximum value of n or x in my integer x, this bit must be set, right? This bit must be set. And if you have a same prefix in x, so before this we have all the bit set in my integer n, because this is the first occurrence of 0 from left to right. So all the values of x which has the same prefix, all the values of x which has the same prefix are going to be greater than n, right? So I need to subtract this count. So for this thing, I will count how many ones we have after the position P. So this is nothing but a set bit, number of set bit minus prefix. These many ones we have. So the value of extra would be 2 power number of set bit minus prefix. So I hope this is clear to everyone. Now let me show you the implementation here. So well, this is the complete implementation, and this is the method that you need to complete. Total ways, it's take a integer n as a parameter, and it will return the possible values of x which lead you to the maximum result of x or n, and the values of x should be less than or equals to n. So this is my total count. So total count is nothing but the number of set bit, 2 power number of set bit, and the extra count will be written by this function extra, and then my answer will be total count minus extra count. So for the extra count, here first I am finding the number of set bits in n, and also I'm going to find the binary representation of n. So this is the function which is going to return me the binary representation of n. It's a super straightforward. I'm not going to explain that how this utility method is working, because yeah, this is super straightforward. You can read some article that how we can convert some integer to its binary, and we are returning it in a form of vector. So now I'm going to start iterating from position 0, that is from the MSP onwards, from MSB onwards, left to right. Cool. And this is my prefix, that is a number of zeros before the number of ones before the first occurrence of 0, and this is my size of this vector. So while the bit is 1, I keep on incrementing the position, and once I get that bit is 0, then I will terminate this while loop, and this variable prefix will store the number of ones. Cool. So this is an edge case. So if all the bits in n is set, then I don't have to subtract anything, right? So in that case, I will simply return 0. So consider the case when all the bits in n are set. So this case, when all the bits in n are set. So in this case, your answer will be 2 power 2 power the number of set bits. Here we do not have any extra. So yes, this is the case. Otherwise, my extra count will be 2 power the number of set bits minus the number of ones before the first zero. Total number of set bits minus the number of ones before the first zero. And finally, I am returning this extra count. So this is the complete solution, and it takes a logarithmic time. Log of n base 2. Now let's try to run this program, or let's try to submit it. But I have already tested. It is a correct solution. So yeah, successfully submitted. Now before discussing the third problem, let's just also discuss its follow-up version. So the last problem of the contest. So in this problem, this is a follow-up version of the second problem. So here you don't need to count the number of possible x. Instead, you need to find the sum of all such x. So let me read the problem statement again. So you are given an integer n, and you need to find all the integer x such that x is less than or equals to n, and the value of x or n is maximum, and we need to return the sum of all such integer x under modulus 10 power 9 plus 7. In the previous case, we need to count the values of x, but this time we need to return the sum of x. So let me give you some example. N is equals to 3 and n is equals to 5. So let's say n is equals to 5. So the binary representation of 5 is 1, 0, 1. So what will be the maximum value of n or x? So that is, all the bits are set after the MSP, that is 1, 1, 1. This will be the configuration of a maximum value of n or x, and this is nothing but a 7, binary representation of 7. Cool. So what are the possible values of x we can have? So I can select the value of x as 2. Yes, I can select the value of x as 2. So 0, 1, 0, the binary representation of 2. And I can also select the value of x as 3. So the binary representation of 3 is 0, 1, 1. So now let's find the value of n or 2. 1, 0, 1, binary representation of 5, then a binary representation of 2, 0, 1, 0. This would be 1, 1, 1, right? Equals to the maximum value that we can have. Then n or 3, so binary representation of 5, then binary representation of 3. So this is 1, 1, 1, the maximum value of n or x. Now, can we have the value of x as 4? No, it is not possible. This will not lead you to the maximum result. So let's find the value of n or 4. This is 1, 0, 1, binary representation of 5, then binary representation of 4, 1, 0, 0. So this is 1, 0, 1. This is 5. This is 5, not 7. Cool. So the value of x is equals to 4 is not possible. Now I already told you how many values of x are possible. Now I need to find the sum. So the idea is again same. First I'm going to find the total sum. And then from this total sum, I will subtract the sum of x which are greater than n. Okay, so here Asutosh is asking, why should all the bits be set only after MSP in X? I didn't get your point, but let's say you have a value of n is equals to 5, and this is a binary representation of 5, 1, 0, 1. So which value of x? So basically, what will be the configuration for the maximum value of n or x? So that is a maximum value of n or x. What will be the configuration? So that is all the bits are set 1, 1, 1, right? So this will be the configuration for the maximum value of n or x. And now I need to tell how many such values of x are possible. ठीक है, तो अभी ये वाला वर्जन सॉल्व करते हैं. Let's solve this version of this version, and I'm going to again explain this thing. So with the same example, but now instead of counting the number of x possible, instead we need to know, we need to find the sum of those values of x. So again, let's say a binary representation of n. 1, 1, 1, then let's say we have 0, then 1, and let's say again 2 zeros and 1. So the configuration of maximum value of n or x would be 1, 1, 1, 1, 1, 1, 1, and 1. So this lead me to the maximum value. ठीक है, so this is bit 0, then bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, and bit 7. So the very first thing, I'm going to count how many total values of x are possible, and then I will subtract how many values of x which are greater than n. So eventually I will get the number of x which are less than or equals to n, and lead me to the maximum result of n or x. So the possible values of x are, to get this result, maximum value of n or x जो है वो मेरा वो कैसा दिखना चाहिए. So the very first thing, at these positions we could have anything, but at this position the bit in n is 0, so we must have 1. For this position I can select any value, either 0 or 1, because result होगा वो 1 होगा, क्योंकि corresponding bit n में जो है वो set है. And at this position the result is 0. We can select any value for this position, either 0 or 1. At this position any value, either 0 or 1. Then for this position again any value, I can pick any value, either 0 or 1. Then for this position we must have 1 to get the maximum value. At this position we must have 1 to get the maximum value. And for this position we can select any value, we can place any value, either 0 or 1. Cool. So the total count is 2 power the number of set bit, because if we have a set bit then the corresponding bit in integer x could be anything, either 0 or 1. So that's why 2 power the number of set bits. Cool. But this time we are not interested in a count. Instead we are interested in a sum of possible values of x. So let's call this as a total sum. So total sum. So this is nothing but these many possibilities we have. Basically this is a count. So now I'm going to find the contribution of each and every bit. So starting with the bit 0. So here in this case bit 0 in n is 1. So we have two possibilities, right? Either I can place 0 here or I can place 1 here. But when I place a 0 here, this bit do not have contribution. I cannot add a weight, right? Because I have placed 0 here. So that's why how many possibilities we have? So this bit, its weight is only contributed when it is 1, right? Then only its weight is contributed. If it is 0, then I cannot add its weight in my answer. So it is equals to total and divided by 2, because we have these many values of x which has this bit 1. right? Total divided by 2. And then multiply with the weight of this bit. So the weight of this bit is 2 power 0. Cool. Then the next bit in integer n is 0. So we all know if the bit is 0, then we must have a bit 1, bit value 1 in integer x, right? So that's why in this case I will multiply, basically I will add total, the number of such values of x are possible, such values of x possible, and multiplied by 2 power 1, right? Then the next bit is again 0. So the corresponding bit in x must be 1. So that's why it would be total how many x possible and multiplied by 2 power 2, the weight of this bit, 2 power 2. The next bit here is 1, right? So the next bit is 1 in integer n. So in my integer x we could have anything, either 0 or 1. But when you place a 0 here at this position, you cannot add the weight of this bit. But when you place 1 here, then yes, we can add a weight of this bit. So how many values of x are there which has this bit 1? So this is total and divided by 2, because equally we have both the possibilities. So total divided by 2 and multiplied by the weight of this bit, which is 2 power 0. And in this way I will find the sum. I will find the contribution of all the bits. If the bit is 1, then the contribution would be total divided by 2 multiplied by the weight of that bit. And if it is 0, then it is simply total multiplied by the weight. So let me show you the implementation for this total sum. So this is the method which we need to complete, and here I am calling this function total contribution, and this function takes the integer n as a parameter. Then total number of set bits, count of set bits, then total count would be 2 power the number of set bits, right? And initializing the weight with 1, and also and answer with 0. So here I'm going to check for LSP. If the LSP is 1, then I will add total count divided by 2 multiplied by the weight of this bit in my answer. And if the bit is 0, then I will add total count multiplied by weight. Here this time I'm not going to divide it by 2, but when the bit is 1, then only I will divide it by 2. Cool. And then I will multiply weight by 2, or I can say weight left shift 1, and then I will remove this LSP, because for the next bit the weight is double. And here I am having the multiplication modulo method that will multiply two numbers under modulus 10 power 9 plus 7. 10 power 9 plus 7. And similarly we have addition under a modulo, so it will add two numbers and under modulus mod, and will return me the result. Cool. So up to this point we have a total sum. Now I need to subtract the values of x which are greater than n. So let's find how many such values of x are there. So the binary representation of n, 1 1 1, then 0 1 0 0 and 1. Cool. And we all know the maximum configuration. So this would be n or x. So the maximum configuration has all the bits set from the MSB onwards. So that is 1 1 1, then 1 1 1 1 1, right? This is the configuration for the maximum value of n or x. Cool. So how many values of x are there which are having value? How many x are there which are having value greater than n? So we all know how we generated the x. So we have generated the x, that is, at if the bit is 0, then we must have 1. We must have 1 in integer x, right? So at these places we must have 1. Cool. Now let's consider the value of x which has the same prefix, right? Which has the same prefix. So all the values of x are going to be greater than n which are having the same prefix. So I need to subtract some of these values of x which are greater than n from my total sum. So for this one, I have two possibility. Either I can place 0 or 1. For this one, only one possibility. For this one, also again two possibility. Either I can place 0 or I can place 1. Right? So for the set bits, I have two possibilities, and for the bits which are 0, I have only one possibility. And let's call this position as a p, or as per my implementation, I called this position as pose. And how many zeros we have before this position pose? So this is stored in my variable prefix. So how many zeros we have after this? So it is a number of set bits. So set bits minus prefix. These many zeros we have after position pose. So the extra count will be 2 power set bits, total number of set bits minus prefix. This is the extra count, right? But I need to find the sum, not the count. So the value of extra sum. So we'll iterate from bit 0. So let me write the bit numbers. So bit 0, bit 1, then bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. So here in this case, the value of pose is equals to 4. That is, value of pose is equals to 4. Or maybe it is not required, because in my implementation, I have converted this into a binary, right? So after calling my method binary, it will return me a vector which is representing a binary representation of n. So in that vector, I will iterate from left to right and will find the position of first 0. And then I will iterate from right to left. So iterating from right to left, and here let me write the indexes. So okay, let me just clear this. So for this one, I have two possibilities, 0, 1. For this one also 0, 1. So this is my index 0. This is my index 0. Then index 1, index 2. So these are the indexes. Do not get confused. Indexes in a binary representation of n. Indexes of a vector which represent the binary representation of n. Then index 3, index 4, index 5, index 6, and index 7. So then I will iterate from right to left. I will iterate from right to left. Cool. And initializing the weight with 1, 2 power 0, which is equals to 1. And now I'm going to check, I'm going to write this thing, that is if the value of I, so here in this case, I declare a variable size, and this size will store the size of my vector. So variable sz, and it is equals to bits dot size. Cool. So I will run a for loop, and I is equals to size minus 1, that is from the last index and up to 0. And if the value of I is greater than pose. So let's first write a case when the value of I is less than or equals to pose. So in that case, what does it mean? So if that is the case, then I know if we have 1, then for the 1 we have only one possibility, right? Because now I'm considering the values of x which are greater than n. So if we have 1, then only one possibility, I must have to place 1 here to get the same prefix. So my extra sum, initializing the extra sum with 0, and extra sum plus equals to, let me change the color. So extra sum plus equals to the weight, and every time I will update the weight. So weight of a bit and multiplied by extra count. So weight multiplied by extra count. Cool. And if that is not the case, that is if the bit is before this position, that is if the value of I is greater than position. So in that case, for zeros, if the bit is 0, if the bit is 0, if bits of I is equals to 0, so in that case I must pick 1 here. I must select 1 for this position. So extra sum plus equals to its weight and multiplied by extra count. This is same as my implementation, and if the bit is 0, that is else wala case. So in this case I need to consider the half, because half numbers will be there whose bit is 1, and half numbers are there whose bit is 0. So if it is 0, then I do not have to add the weight. So extra sum plus equals to the weight of a bit and multiplied by extra count and divided by 2. This is same as the previous explanation. And every time I will update the weight. This is the only thing which I need to update. So weight is equals to weight multiplied by 2. Weight multiplied by 2, because at the LSP the weight is 2 power 0, which is 1. So that's why here I have initialized the weight with 1. Then multiplied by 2, 2 power 1, then 2 power 2, then 2 power 3, and so on. So this is the way how we can find the extra sum. And then my final answer will be total sum minus extra sum. So let me show you the implementation for this extra sum. So now I am calling the method extra for integer n, and this will return me the extra sum, that is sum of values of x which are greater than n and lead me to the maximum value of n or x. So first I will count the total number of set bits, then the binary representation of n, then the size of this vector, then this is my position which is start from 0, and this is my prefix, how many ones we have seen before the first 0. Then while the bit is 1, I will increment the position and increment the prefix. Then this is the base case which I already told you in the second problem. If we do not have any bit 0, so then all the possible values of x are less than or equals to n. So the value of extra sum would be 0. So return simply 0. Otherwise, this is my total count, which is 2 power count set bits minus prefix, and initializing the answer with 0 and weight with 1. Then iterating from LSP to MSP. So If the value of I is less than or equals to pose, then I will add total count multiplied by the weight of a current bit in my answer. Otherwise, if it is in a right half, then I need to check. If the bit is 0, then only one possibility. So add total count multiplied by the weight in your answer. And if the bit is 1, then I have two possibilities, 0 or 1. But I only need to consider those values of x for which I have placed 1. Because when I place 0, the weight of this bit do not have any contribution. So how many possibilities for that we have? Total count divided by 2 and multiplied by the weight. And finally, before moving to the next bit, I must have to multiply the weight by 2. And finally, I am returning this answer, that is extra sum. This answer is nothing but extra sum. Extra sum. Cool. So yeah, this is the complete explanation from my end. The time complexity would be n, sorry, not n, but log of n base 2. So coming to the last problem of the contest, pick the chocolate. So in this problem, Geek is playing a game on a number line, on a 1D number line, and he starts at position x is equals to 0 and moves 1 unit left or right in each second. And the game has the following rule. There are boundaries at coordinate x is equals to minus b and at coordinate x as x is equals to b. Means Geek cannot go beyond these points. We cannot go beyond the coordinate minus b and we cannot exceed the coordinate plus b. And but we can stand on coordinate b and minus b. And there are chocolates placed at coordinate minus c and plus c. If the geek reaches a chocolate's position, he collect it instantly without wasting extra time. And your task is to determine the number of distinct ways geek can collect at least one chocolate and return to x is equals to 0 after n seconds. And since the answer may be large, so you need to return the answer under modulus 10 power 9 plus 7. So let me explain you this sample test case, but I guess it is very straightforward. So here the value of n is equals to 2. That is, we can perform two moves here. And the boundary is at coordinate minus 10 and plus 10. The chocolate is placed at coordinate 1 and minus 1. So there exist two distinct ways in which we can collect a chocolate and again return back to the position 0, the starting position. So the first way, from x is equals to 0, from the coordinate 0, I will take a move and move in forward direction and will go to the coordinate 1 and then again return back, collect a chocolate from coordinate 1 and again return back. So this is one way. The second way, from position 0, take a move in a backward direction to the coordinate minus 1 and again return back to the coordinate 0. So this is another way. So in total there will be two ways are there. So now let's analyze the constraint. So the value of c is always less than or equals to b. That is, we must have a chocolate before the boundary, and which is very obvious, and can be up to 10 power 5. And the value of n can be up to 10 power 3 only. So this is really very important thing, that the value of n can be up to 10 power 3 only. So with these constraints, we can apply a dynamic programming logic. So the name of the problem, pick the chocolate. So this is a pretty standard problem, I can say. The value of n here can be up to 10 power 3. So we can simply apply a very standard dynamic programming solution. So for this thing, let me define a state. So recur and n comma position, and basically the number of moves which we are left with, and position will simply the current position, and another parameter pick, whether I have picked the chocolate or not. If it is 0, then we have not picked the chocolate so far, and if it is 1, that then it simply means we have picked an chocolate. And with these three parameters, I can uniquely determine my function. So let me write the definition here. So number of distinct ways to collect at least one chocolate from either coordinate C or minus C. If we start from position pose, the second parameter, and we have n moves. Now this variable pick is equals to 0 is equals to 0 if we have not picked the chocolate so far. Or what I can say, what I can say, the value of pick is equals to 0 if we have not picked the chocolate so far. Yes, if we have not picked the chocolate so far, then the value of pick would be 0. Else else it is equals to 1. Cool. Now what would be the transitions here? So the very first thing, what will be my answer? What will be my answer? So my answer is equals to recur of n, the initial value of n, the initial number of moves which we have, and position 0, starting with the position 0. And then so far we have not picked any chocolate. So that's why the value of this argument pick is 0. Now let me write the transitions here. And then I will discuss the base case and some boundary cases. So here the very first thing, if at position if the position P is equals to C or minus C, so then I will mark this variable pick as 1. So if position is equals to minus C or position is equals to C, then what does it mean? It simply means we are standing at some position at which we have a chocolate. So now I'm going to mark this variable pick as 1, right? Do not get confused here, because now we are going to start with the position pose, and the state from which we are coming. So far in those state I have not picked any chocolate. So if at the current position we have a chocolate, I'm going to pick it. I will pick it, right? And then the transition, let me write the transition here. So recur of n, pose, and pick, the new updated value of pick. It is equals to, for every position I have two options. If we are left with some move, I can either take a move in a forward direction or we can take a move in a backward direction. So recur of n minus 1, the number of move will reduce by 1, then position minus 1, and the new value of pick. If at this position we do not have a chocolate, then it would be 0, remain 0, otherwise 1. If at this position or at previous some position we have a chocolate, then recur n minus 1 and position plus 1 when we take a move in a forward direction, and the new value of pick. Cool. And make sure to take the answer under modulus 10 power 9 plus 7. So 10 power 9 plus 7, this will be the transition. Now what are the base cases here we have? So the very first thing, if the position is less than minus p, that is if you go beyond the boundary, then it is not a valid position, right? So in that case I will return 0. So simply return 0. Or if the position exceeds b, so if the position is greater than b, so again the same thing, if you go beyond the boundary, then it is not a valid position, so I'm going to simply return 0. Cool. Now if n is equals to 0, so if n is equals to 0, now we cannot perform any move. So in that case, what I should return? So it is clearly mentioned in the problem statement, that is we must have to return 2x is equals to 0 after exactly n seconds, or I can say after exactly n moves. So that's why I will return true. I will return true if position is equals to 0. I again return back to the origin, and we have picked some chocolate. So I will simply return a boolean result, that is position is equals to 0. This is the first condition. We must return back to the same origin, and we must have picked the chocolate. Then only I will return true. Otherwise, I will return false. So this is the complete solution. Now the problem with this solution, as you can see, the we are subtracting 1 from the position every time, and we are making a call. So the value of this position can be negative also. The value of this position can be negative also. So how we can handle this case? So this is a very standard technique, of using offset. So the value of position may be less than 0. So how to handle this case? Because if you memorize it, then we do not have a negative indexes. So this is where we can use some offset. So offset basically means I'm going to add some integer as an offset to get rid of this condition of a negative indexer. So we all know the value of n can be up to 10 power 3 only. So now I'm going to use an offset 1000. So that's why I'm in my memorization I will use in my memorization I'm going to memorize pose plus this offset 1000, so that I know the result of this value, the result of this expression is always greater than or equals to 0. And this is a very standard technique using offset to avoid the negative indexer. So this is the complete solution. So I will create a DP table, because there is an overlapping subproblem which I need to memorize. Then the value of n 1000, so 101. because at some point of time I also need to access the index 1000. That's why plus 1 to be on the safer side. Then here we would have 2000. Yeah, 2000 is enough, right? And because 1000 values of n and plus 1000 for this offset, and two possible values for this pick. So this will be the time complexity. The time complexity here is 10 power 3 multiplied by 2 into 10 power 3 and multiplied by 4, which is multiplied by 2, the possible values for pick. So the overall time complexity is 4 multiplied by 10 power 6. So yeah, that's the complete solution. Let me show you the implementation here. So this is the method that I need to complete. Then here I'm having instance variable, boundary and chocolate. Then I'm updating this boundary with B and a chocolate with C. Then filling the DP table with the -1, and then calling this function recur. N, the number of moves we have so far, and current position, and whether we have picked the chocolate or not. So this is my base case, kind of. If we reaches out of boundary, then I will return 0, because this position is not valid. And if we do not have any move left, then I need to check if we are at position 0 and we have picked a chocolate, then only I will return true. Otherwise, I will return 1. Otherwise, I will return 0. Cool. Otherwise, if we already know the answer for this state after adding an offset, then I will return the answer. Do not calculate it again, because a super straightforward dynamic programming. Otherwise, if the current position has a chocolate, then pick it. So pick is equals to 1. Then call the recursive function, and -1, the number of moves will reduce by 1. And now I'm going to make a move in a backward direction, so pose -1. And if we make a move in a forward direction, then also the number of move reduced by 1, and take me to the next position in a forward direction. And make sure to take a mod, and finally memorize it. So let's try to submit it. And successfully submitted. So these are all the 4 solutions of the today's weekly contest. So, well, I hope everyone has you guys have learned something new. So that's all from my end. If you have any query, then do let me know in the comment section, and make sure to write your feedback so that we can improve the upcoming problem set as well as this post contest analysis. In C++ operation, Boolean operation will return int. Yes, this is a typecasting, Arani. Integer Boolean can be typecasted to integer. All right, everyone. So thanks for watching this stream or this recorded session, and have a good day.